In section 11.3, we learn about a new type of chi-squared distribution test that we can do, and this is the test for independence. The chi-square test for independence is used to determine whether there is an association between a row variable and a column variable in a contingency table constructed from sample data. The null hypothesis in this case, in these types of tests, is always that the variables are not associated. In other words, they are independent. And so that will be our null hypothesis every time. The variables are independent. The alternative hypothesis each time will be that the variables are associated or they are dependent. So that's going to make this pretty easy for us to identify the null hypothesis and the alternative hypothesis. The expected frequencies in the chi-squared test for independence. To find those expected frequencies in a cell, when performing a chi-squared independence test, we multiply the cell's row total by its column total, and then divide that result by the table total. In other words, and we have to do this several times, we have to do this for each cell in our table, we're going to multiply the row total for the cell that we're looking at times the column total for the cell that we're looking at divided by the total for the entire table. So I'm going to show you how to do that here in a little bit, but that's how we find expected frequencies. Example 11.3, in a poll, 883 males and 893 females were asked, if you could have only one of the following, which would you pick? Money, health, or love? Their responses are presented in the table below. So you can see those things and notice what we've got related here, and you got the totals listed, but really the columns are money, health, and love, and then the rows are men and women. So the idea behind the independence test is we're going to test to see if the men's and women's answers are different when we look at money, health, and love, or if they're the same, if they're independent, if it doesn't matter which gender they are. So we are going to determine the expected counts within each cell, assuming that the gender and response are independent, because remember, that is our null hypothesis. So as you can see, I already have the expected counts there, but I'm going to show you how to do this. So let's say that we are dealing with this first cell here, the one for money and men. What we do is we take the row total times the column total. Now, if those totals aren't given, you just have to add up 82 plus 446 plus 355, and then you're going to multiply that times the 82 plus 46, and you'll have to come up with your own totals if those totals are not given to you. So for us, we are going to multiply 883 times 128, and then we are going to divide by the table total, which is 1,776. And you'll notice we get this number, we are going to have to round it off in the answer total there. They round it off to one decimal place. So we'll go ahead and we can see that that is 63.6. And so that does match up with the number we have there. To go to the second cell, we will use, again, this time, our row total. Well, I guess our row total is still going to be 883, but our column total is going to be 1,020. So we will take the 883 times the 1,020, and then divide by the 1776, and we get 507.1 if we round that one off. And so we can see again that does match up with the total they have there. And when we go to the next one, we will move over to the next column. So we'll be doing this cell, and we're going to use those two totals, the 883 for the row total times the 628 for the column total, and we get that number, I forgot to divide it, divided by 1776. And as we round off the nearest tenth, we get 312.2. And so we can see all three of those numbers match up just fine with our answers there in the other table. So then we'll go to the next one. So now we go down to, that was the men row, and now we're going to go down to the women row. So we're going to find this cell, and we do the same process. We're going to take the 893 times the 128. Let me get rid of that. And so 893 times 128 divided by the 1776. And we get 64.4 if we round that off. Okay, and if we go to the next one, move over to the next cell, and we will have that 574 cell location is the one we're looking at. So we will multiply the 893, the row total, times the 1020, the column total, and we will divide by the table total, 1776. We get 512.9. And one more time, just to finish showing off the process here, we're going to find the answer that's going to go into that cell for the expected values, the expected count, and we're going to have the row total 893 times the column total 628, and we're going to divide by 1776, and we get 315.8 if we round that off. So 315.8, and we can see that all of those values match up just fine with our answer for those expected totals. So that is the process we use. It takes a little bit of time, but it's not difficult. It would be more challenging if you didn't have the totals already given to you. But if you didn't, what I would suggest is just use your calculator, add up the 82 plus the 446 plus the 355, and then make your own column for the total. And then do the same thing with these, 46 plus 574 plus 273, and make that one. And then you do the same thing for the rows. Just add up, or the columns, I mean, add up those two, add up these two, and add up these two. And that way you've got your own total row and column values. And then you can add those up to find the total for the whole thing. And that way you have those numbers handy rather than having to add them every time you do the problem. So the steps for testing independence with a chi-square test for independence is this. We will test the association or the independence of the two variables in a contingency table. And we will use the steps here. So determine the null and alternative hypotheses. We already mentioned the null hypothesis is always going to be that the row and variable column, the row variable and the column variables are independent. The alternative hypothesis will always be that the row variable and the column variable are dependent. So in other words, your null hypothesis is, like in that last example, that the men and women basically chose the same percentage of choices when you talked about love, money, and happiness? Health, that's what it was, health. And it didn't matter whether they were male or female, those percentages were about the same. The alternative hypothesis would be that they're different, that men significantly choose a different category than the women do. And so that's what we're testing here with a test for independence. After we have done that, we are going to decide on a level of significance, alpha, depending on the seriousness of making a type 1 error. We will calculate the expected frequencies, which we just did that example, how to do that, the expected counts for each cell in the contingency table. That's honestly going to be the hardest part of our job here. Then, part B, we will verify the requirements for the chi-squared test for independence are satisfied, and they are the same as the chi-squared test that we used in 11.2, and that is that all the values are greater than or equal to 1, and no more than 20% of the expected frequencies are less than 1, or sorry, less than 5. Part C, compute the test statistic. Again, we're not going to have to worry about doing that because our calculator will do this for us. But that is the formula that we had learned of how to do that, and it's the same formula we had in the last lesson. The p-value approach is the one that we will use because we can do that on our calculator pretty easily. We're going to compute the p-value from our chi-squared test. We're going to compare the p-value with alpha. If p is less than alpha, then we reject h sub 0, the null hypothesis, and there is enough evidence to support our alternative claim, h sub 1, and the result is statistically significant. If the p-value is greater than alpha, We fail to reject the null hypothesis, and there is not enough evidence to support our alternative hypothesis. Again, remember what our picture for these chi-squared tests look like. All the values are positive. It is skewed to the right. And so that kind of gives us a picture of what's going on, but we want to make our conclusion regarding the claim and then interpret that in context of the scenario that we have been given. The calculator steps for the chi-squared test for independence, this is going to be a little bit different. So what we have to do after we have our two tables, our two contingency tables, one with the actual counts and one with the observed counts and one with the expected counts, we will access the matrix menu. And I'll show you how to do that in just a second. Then we will highlight the edit menu. We have to use our arrows to go over to the right. And then we'll select number 1 for matrix A. And then we'll enter the numbers of the rows and columns for the contingency table that we're using. And then we will enter the cell entries for the observed matrix, and then press second and quit. Then we will do the same thing. Oh, I guess we don't even have to enter the matrix for the other ones. I thought we did. We're going to press stat and highlight tests, and then select C, the chi-squared test. Yeah, we didn't enter the B. We do have to enter the expected ones in for B. So yeah. So with the cursor after the observed, enter matrix A by accessing the matrix menu, highlighting the names and selecting number 1 for matrix A. Then with the cursor after the expected section there, enter the matrix B by accessing the matrix menu and highlighting the names menu there and selecting number 2, B. And then highlight either calculate or draw and press enter. I took that out and I forgot to fix it again. So highlight or draw and then press enter. So example 11.4, in our poll, 883 males and 893 females were asked if you could have only one of the following. It's the same example we did in 11.3. And notice we have our observed values and our expected values both given to us here. We're going to test the claim that the gender and response are independent at the alpha equals 0.05 level of significance. So the first thing I'm going to do here is identify our null hypothesis, as we normally do, and that is that the categories are independent. Then the alternative hypothesis is the categories are dependent. Okay, and we've already generated our table for the expected count, and we were given the table for the observed count. So let's go ahead and go to matrices. So the matrix menu is going to be the second button and this inverse button right here. Nope, that's the wrong one. I pushed the wrong one, sorry. Second inverse right there. That brings us to the matrix menu. Now notice, you've got 3 options here, names, math, and edit. We need to go over to the edit menu. And we're going to select number 1 for matrix A. And we are going to look at this, and this is something you may not know about matrices, but when you enter in the values here for the dimensions, we have 1, 2 rows, that's the first number, so 2, enter, and we have 1, 2, 3 columns, that is the second number, 3. And so once you put those in, you can see I've got a matrix here that looks like our table. So then we will just enter these in, 82, enter, 446, enter, 355, enter, 46, enter, 574, enter, and 273, enter. Oops, I didn't get the 273. Let me type that in again, 273, enter. Okay, so now we should be good. We're going to quit to get out of that menu, and I'm going to try it here without entering in the expected values to see if it will work. So we're going to go to Stat and over to Tests, and we're going to go down to the chi-squared test, which is right there. We're going to push Enter, and notice it already has the observed value for matrix A and the expected values in matrix B. So I'm just going to go down to calculate and see what happens if it gives us an answer. I think it does. So I'm going to go back and check. Second inverse. Yeah, notice it actually filled out matrix B for us. So let's go take a look at matrix B and see if it matches up with what we've got. So 63.64, 507.13, 312.23, 64.36, 512.87. Yeah, that's matching up. It's keeping more decimals than we had, but that's just fine. So we don't even have to type in the expected count matrix. We can just let the calculator do that work for us. So it's a little secret. If you are just finding the expected counts, you can actually do it this way, and it will do that math for you. Let's go back and let's see if I can bring that back up here. Nope. Okay, so stat over to tests, since I lost my information here. There it is, and hit enter. Go down to calculate, and we get this. So notice it's telling us our degrees of freedom is 2. I'm not sure how it's calculating that because that's not usually how we do it, but anyway. Notice our chi-square value is 36.84 if we round off to 2 decimal places, and that would be our test statistic. Our p-value, now again, be careful with this p-value. I see people making mistakes on this all the time. P cannot be bigger than 1, and this p-value looks like it's bigger than 1 if we're not careful. We have this scientific notation, e to the negative 8th. That actually means you've got 7 zeros and then finally that 1, which means usually what we'll put in there, because it's not saying it's impossible, so we'll usually put in 0.0001 just to keep our 4 decimal places and show that it's not impossible. But anyway, our goal now is to compare P with alpha, and since alpha is 0.05, P is definitely less than that. So that means we reject the null hypothesis, and therefore there is enough evidence to support the claim that the categories are dependent. Because remember, Because remember, our assumption was that they are independent, and based on our values that we got here, we're getting that they are dependent. So notice most of the women are actually picking health, and actually most of the men are too, but a lot more of the men, as far as percentages, are picking money and love, but a much greater percentage of the women are picking health for their highest value there. So that's how the test for independence works, and really you do the same thing pretty much every time, and it's nice to know now that since we're using the calculators, we don't have to do all that math to figure out the expected values on our own. We can let the calculator do it for us, and but that's the process we go through, and it's pretty much, like I say, it's the same every time. You'll just have different sizes of matrices to look at. That is the end of section 11.3, so you can go ahead and work on those 3 problems. They will take a little bit of time to get everything figured out and stuff and figure out how to use your calculator, but make sure you're practicing on that so that you are prepared when it's time to have to do that on your own.